All right. Does the mic work? Yes, cool. Okay, so welcome everyone to my presentation on mazes. So if you hear my voice vibrating a little or see me shaking, that's definitely not me being nervous, just me being very excited to talk about mazes every day of my life. So you see this beautiful intro. I'm not a designer myself, so sometimes I ask my girlfriend for a bit of help on like making something look nice. So if you ever see something look nice, that's probably not my work. So the 1 trillion pixel maze. Whenever I say that I do stuff with mazes, people ask me, why do you do that? And that question is a little hard to answer. So I made a bit of a drawing to take you through the journey, how I got into this and how I got.
It's made by yourself, isn't it?
Exactly. That guy understands it. So when I was still in school, quite a few years back, we had a class called algorithms, and at the end of that semester, you could choose an algorithm you could implement, and you would get graded on that. So I was working on the red-black tree algorithm, and as you can see in the drawing, my face didn't look very happy. A friend of mine, however, was doing something else. So I moved over, checked out what he was doing, and he was doing something with mazes. So I asked him, hey, can I maybe have your code and maybe take a look at it? So this was about 13, 14 years ago, and I've been like tweaking it a little here and there, and then now we are basically here, and I'm doing a presentation on it, and I think he's long forgotten anything about it. The agenda. So first I'll start with the question, what is a maze? Then I'll talk a bit about my own goal I set for myself regarding the size of the maze. I want to talk a bit about the biggest maze that I created and also how to create a maze as fast as possible. And then I'll end with some of the spin-offs. And if I have some time, maybe I can show some cool demos as well. For the biggest, I've divided it up into 3 sections. So I start on like the easy things I did, then medium, then hard. And then there's like this XXL super hard thingy. And basically, I did the same for the fastest maze. So let's start with the initial question. What is a maze? The definition of a maze in my whole code works like this. You either have a cell that is a wall, or you have a cell that is walkable. There's other ways to define a maze, but this is something that works quite nice with algorithms and I think looks nice. Next, you can see the path. It always starts at the top left and ends at the bottom right. And the further you get into the maze, the redder it gets. And the reason for the path being a gradient, you'll probably see later once the mazes get a little bigger. That gradient thing is a bit important to keep into your mind, because for every position in the path, I also store a single byte that determines how far we are from the beginning towards the end, so that I can determine the color. Maze generation. There's multiple maze generation algorithms, and I specifically chose the backtrack algorithm. The reason for that is simply because it generates the coolest looking mazes. If we have some time at the end, I'll show you some of the shitty algorithms. The way that the algorithm works is basically every step we do is we go into a random direction, and we store the previous positions to get back to the beginning. As you can see, it's going now. There's nothing going wrong, so we just try to keep moving into a direction until we get stuck. I know it will be a few more steps because I've seen this video a few times. It might go down now. Oh, yeah. Okay, so now you saw it getting stuck. Then what it does is it backtracks to the first possible position where it can go to a new direction. It goes that direction and it continues. It should be, yeah, okay. So you could see it doing that again, then it did it again, and now Once it reaches this, it backtracks all the way to the beginning, and we have a maze. The other thing that we have is pathfinding. So for pathfinding, the algorithm looks quite similar. It's actually a depth-first search algorithm, where we just try to follow the path that exists. And whenever we can, whenever we find a junction, we just prefer to go to the right or to the bottom. And the reason why this works so well is because all the mazes that I generate with that backtrack algorithm have only one solution. From any point to any other point, there is only one solution. So if this algorithm finds a solution, then we know that's the only solution that exists, so it must be the fastest one as well. The gray areas you see here, those are the areas where the pathfinding algorithm tried to go into a direction, and in the end, it wasn't the right one. But you see there's only a few number of mistakes it made. Of course, if the mazes get bigger, it makes a bit more mistakes, but the overhead of an algorithm like A*, in my case, took much more time than just doing it as dumb as possible. So, with this knowledge, I set a goal for myself to basically create the biggest maze and do it as fast as possible. These things, however, don't really go hand in hand, so I chose to separate them into two different sections. And with that, I wanted to give you guys a bit of a sense of scale. So who knows this as like the Windows 95 maze screensaver? That was my first introduction to mazes, and I could look at this for hours. This actually isn't it. This is my own implementation of it. So you can actually just remove the roof and float out with the camera. You can see this cool guy casually strolling through the maze. That is the path he needs to take, so he has a little bit of ways to go, but as you can see, he's happy, he's going towards the end of the maze. So this maze is also generated with the backtrack algorithm and has a size of 32 by 32. Once he reaches the end, I'll scale it up a little and I'll show you guys what a bigger maze looks like. So in the top left, you can see the current size. So I'll now increase it to a bit bigger. And then I'll let you guys enjoy the view. So this is 2000 by 2000. So you can see it in the top. The total path length is 285,000 steps. In the video recording, I tried to fly back to the dude, but as you can see, it even took me a bit to find the man. Oh, I already saw him. But yeah, this guy has some ways to go, basically. This was 2048 by 2048, which is 0.00038% of the 1 trillion pixel maze that we're going to make. I will not show that in 3D because, sadly, there is no computers yet that exist that can show that. Let's start with the first implementation. So this is basically the baseline which I started with all these years ago. And there's probably some like really stupid things in here that you might have done differently at the start. Again, I was young, I didn't know, but I'll take you through the whole process. So what I started with was I defined the map as an enumerable, or which could either be a wall or walkable, and I defined the path of an array of maze point posts, which all have an integer for the x and y, and the relative position that I told you about. So the maze itself, if you store it like this, takes 1 gigabyte, and the path, which we also need to store from the beginning to the end, takes about 112 megabytes. The easiest fixes were, as you might already know, is an enumerable underwater by default is an integer, so you can just change that to a Boolean, since we only need to store whether a cell is walkable or not. A bool also, though, isn't really efficient either. since you have something called a bit array. So a bool still stores every value in 1 byte, but if you use a bit array, it actually only uses 1 bit per cell. So then, for that part, we're already reducing the memory we need by about 32 times. Some more easy ones is actually making sure that it runs on 64 bits. So in the old .NET Framework days, you still had to do this explicitly. And also make sure that to even run it in some reasonable time frame, I had to do a release build, of course, and make sure that it ran without a debugger. Because especially in these cases where the operations are just mathematics, these things really stack up. Another thing back from the .NET Framework days was this one. So in .NET Framework, you couldn't use objects larger than, I think, 1 gigabyte by default. And if you set this to true in your app.config, then it magically works. Then the last thing of the easy ones that I needed to do was I wanted to store this maze, but for some reason, Microsoft doesn't really take into account my problems. So the whole system.drawing thingy doesn't work with images this big. So I still don't understand them. But I found another library that does understand people like me, and this writes images row by row. So what I could do is I could take the whole maze, take the path, go pixel by pixel, write it, then go to the next line, etc. And that worked. So with that, the first steps were gone, and I was able to make the 64 by 64,000 maze. If you can see here, that 2K maze thingy, that was the thing I just showed you in 3D, just as a reference. If you open this thing, back in the days I couldn't, now I can. If you open this, it will open in Windows Photo Viewer, and it will take 25 gigabytes of memory. It actually runs really great, though. You can zoom in, drag it, so great tool. But I wanted to go bigger, obviously. So I basically calculated the data again for the next step. So if I would do it like this, then the maze for the 131,000 would be taking 2 gigabytes of memory, the path 5 gigabytes, and I wanted to see what other optimizations I could do. As you can see, the way that I calculate the path size is just I generated a maze, could be a bit different. Did it times 9, since we have two integers and 1 byte value. And that's the total number of bytes it will take for the path, I thought. I wasn't correct, however, because in C#, if you define a struct like this, it will, I'm not even sure how it's called, but it will basically take a layout where everything is layouted on a 4-byte spectrum. So the last byte didn't take 1 byte, it actually took 4. But you can do something like this, and that allows it to actually shrink it down a little to the actual size it needs, and then it only takes 9 bytes. Then, why use memory when we actually have a hard disk? So what I did was I changed the implementation a bit, that rather than looking into the memory for every whether a cell is walkable or not, I just looked it up on the hard disk. So I ran that, and that, of course, took months to run because it was way too slow. Then I thought, hey, maybe I can divide the maze up into like a grid, and then every time the generation algorithm hops from one grid or one tile, whatever, to the next one, we load that new tile from the disk, and then continue with generating there until we hop over to another one. I put a bit of caching in there that we stored the last 20 cells into memory, and that actually worked quite well. Of course, it's a bit slower, but hence me splitting the big one from the fast one. With these optimizations, even on the older computers, I could generate a maze of 128K by 128K. So I was quite happy. So I opened it. And of course, there's no single tool in the whole world who can open a maze this big. So I had a PNG image, which was starting to become quite significant in size. But I had no way to even see whether what I just spent the last few weeks on did even do anything. So I had to figure that one out. And what I found is people think about me, apparently. So someone created an application called GigaPan, and that is specifically made for actually not mazes. The reason why they made this is because you can, there is people that go outside and they can put like a tripod down, they put a camera on it, and then the camera takes thousands of pictures, like every few degrees, then they stitch it all together, and then you can have like a picture of, I think there's one from Shanghai, where you can zoom in right into someone's bedroom and zoom all the way out again. This is a way better use, of course. So I could view it, but I still wanted to go bigger. Next step, the 512K maze is how I call it. This would take 34 gigabytes of memory, but split between the memory and the hard disk, which is fine. The path, however, started to become a problem now, because 59 gigabytes of RAM for just the path, that wasn't really scalable. So I had to think of a bit of a solution how I could deal with that. And I did. So the way, again, that the backtracking algorithm works is every time we create or we just store the path from where we are now all the way until the beginning. What we can do, however, is if we create a junction, we only store where we came from. By doing that, we basically have 4 directions, left, right, down, and up, and we would only need 2 bits per direction to store where we came from. So by doing that, a maze that looks like this, which normally has like 200 steps from the start to the finish, we would now only need 13 directions for every junction we see. So if you look at this, we can see, for example, here we would just follow the path back or forwards, however you want to call it. Here's a junction. We see the direction right, so we take a right here, and then we just continue. The problem with this is, though, that once we want to save the whole path, we still need to figure out what color we need to make each cell. So at some point, we need to make some kind of translation between the directions and the actual cells that we want to color in. So what I thought of is within C# we have the very cool enumerable thing. And you can do a yield return where you can dynamically basically create a whole list of the path and then do all kinds of stuff with that. So what I did was I created a method. Yeah, all these I'm not very good at naming things, but that's fine. So I defined this method. You pass in the map, you pass in the directions, and then it will basically just loop over the whole directions and return the whole list of the whole path. If you do this thing and do that to list, then you still have the same problem. You still need to use the whole 60 gigabytes of memory to store it. But since it is an enumerable, what we can do is we can divide up the maze into chunks. I think I divided them up into chunks of 4096. And we just filter the whole path array only on that first chunk. Then we save everything there. Then we throw it away. And then we basically run through the whole enumerable again for the second chunk. What I noticed, though, was that when I did this, especially in the larger mazes, some chunks had a lot of path data, and some other chunks only had a bit of path data. If I had to go through this whole directions to path thingy like 50 times, it would take an incredible time. So what I did instead was I made a path analysis thing, which basically determined how much path steps we have per chunk of 4096. Then we can multiply that by the size that every path step takes. And then we know that for every chunk, how much memory we need. We also know how much memory the machine has that we run this on. So then we can start combining things. So let's say the first chunk has 100, or let's say 2 gigabytes of path data. The second chunk has 5 gigabytes of path data. Our machine has 10 gigabytes of memory. Then we know that we can probably do these two at once, then throw it out, and then continue to the next section. And that actually worked quite well. So that allowed me to create the 512,000 maze. Just for reference, that there is the 2K maze, which we saw in 3D. And I have a little demo on this one, on GigaPan. Even my laptop is afraid of opening it. Okay. I don't know why. You know what? I won't make it full screen. Okay, so what is always fun to do is just take a bit of an area where the green and the red are close together, and then start zooming in a little.
It's like zooming into mountain random.
Yeah, exactly. So there we go. So as you can see, the green and red, for example, they look really close, but in reality, they're probably a billion or so steps away from each other. And as you can see now, what is now like a screen-filling bit of maze, if we zoom out, we'll probably not even be able to see that speck anymore. But fun, right? Okay. But why stop there? What a good question. But what's next? Always use animations, right? That's what we learned. The 1 million pixel maze. So, if we go to these stats again, it would take about 137 gigabytes split between memory and hard disk. The path, if we would compute it in total, it would take about 168 gigabytes. But of course, the algorithms that we now improved, they scale quite well. This should all work. So I wanted to run this. It would take about 2 weeks to run. Would require about 1 terabyte of space for the maze plus the output image. And to run in a bit of a reasonable time frame, use about 14 gigabytes of memory. Again, this is a bit in the past, where this was still quite a lot. Since I usually also try to do other things at my computer, important things like playing games and other things, I didn't really want to give my PC away to mazes for 2 weeks. But there's a solution as well, as your credits. However, there was still a problem. I only get 130 euros per month from Microsoft. And to run this virtual machine, it would take about 200 euros to run for a whole month, because the whole thing takes longer than 2 weeks to run. I had to think about how to solve this. And me being Dutch and from Zeeland, which is like the Dutch of the Dutch, they don't like to spend money. But I had a solution. What if I turn the machine on halfway during August, then my credits will run out by September, but I get another 2 weeks. That's what I did. So a few weeks later, I had the mega terror maze dynamic path with tiles no color map.png of 382 gigabytes. But the stupid GigaPan doesn't support images this big. What kind of software do they make? So I thought maybe this isn't even a problem with PNG, but this is or not a problem with GigaPan, but this is a problem with PNG, because I could imagine that the guys creating PNG didn't think about me as well. So I rewrote everything to TIFF. Another few weeks passed, created the megaterror maze dynamic notepad.tiff. 211 gigabytes, so TIFF is definitely better. But nope, it still crashed with some weird kind of error. So I was stuck again. What I did find out, though, is that there is a tool, basically something similar to like what Google Maps use, where they have like very detailed images, and the further you zoom out, the less detailed something becomes. So I thought, okay, I'll just host that. They suggested a tool called libvips or something, which can take your big image and then divide it up into smaller and smaller levels. So I ran that, and of course, that stupid tool also couldn't open my image. So I was stuck again. And basically, the only way to fix this was creating my own tool that did it all myself. So within my company, we call this yak shaving. So if anyone has ever played Factorio, where you basically want to build an oil field, and then you figure out that to do that, your steel production is empty, and then you go fix that, and then there's an attack somewhere, and then, yeah, you're not doing the thing that you're solving. That's yak shaving. So I built that tool. That basically takes the, I also had to like output the lowest level images into images of 256 by 256. Then it would take 4, scale them up, create a new one, and then just do that like a pyramid. And that eventually worked. So with that, the 1 million pixel maze existed. And I'll show you that as well. Right, so here, let's just take another section where we zoom in a bit. I can make this full screen because this is, of course, way better than the GigaPan. And we can zoom in further. So yeah, this is basically the 1 million pixel maze. And again, I'll zoom out a bit, because it's always amazing to look at. Isn't that fun? I could do this for hours. And you can too, if you just open this link on your phone. Okay. But of course, we are nerds, we want to see some stats. So I did improve a few things with the whole process, so that whole Azure thingy wasn't needed every time anymore eventually. But let's see the stats. So the generation time for the maze took 18.5 hours. So that's just the maze itself. Finding the directions, that's the thing that we do once, takes 5.4 hours. There is a total of 577 million directions. So that means if you would walk through the maze, you'd have to choose the right path 577 million times. The directions only take 144 megabytes. So that was an insane improvement if we compare it with the 168 gigabytes, I think, the whole path would take. So finding a specific section of the whole path within the maze based on those directions would take about an hour, and we have to do that for every set of chunks we start saving. The total path length was 18 billion steps, and I think I calculated it once. If you would like take 4 steps per second, it would take about 200 years to go from beginning to the end, unless you make a mistake. Saving it to an image takes about 62 hours. So again, the path analysis that I built sped it all a bit up. And we managed to do it in like 22 chunks. So 22 times it did that whole path finding direction thing. And then it resulted in 16 million images on the lowest level. Windows doesn't like opening that folder, by the way. So I just had to assume that they were all in there. The image pyramid thing it takes the lowest level, then builds a level above that, builds a level above that. That took another 2 days to run, but then I ended up with a total of 22 million images for a total size of about 400 gigabytes. I also added like the logs, just because it's cool. And here you can see like the different chunk sets we went through. So for example here, it started at row 0, then up until row 72,000, we did all those in one go. We generated them, sorted the path, saved it, combined them, blah. So that's everything regarding the biggest maze. But now I wanted to go to the next section, which is creating a maze as fast as possible. Who made this? Me, not my girlfriend. So I started with a beautifully designed application that I use for testing. You can even see the blue buttons that actually generated that 1 million pixel maze. So it was built in .NET Framework 4.8, and the default benchmark I always use is like the 16,000 by 16,000 maze. The initial version, it took about 3.27 seconds. And I wanted to see how I could further optimize that. So initially, simply converting it to .NET Core already gave me a bit of a performance step, and also this one. So I basically implemented my own version of like the cell storing thing, and if you go this low level, then every call you make to another method is quite the overhead. So if you do something like aggressive inlining, it will actually inline the code within the calling method, and that makes it all quite a bit faster as well. Then, another issue I had was I always like to see things and also like make it as fast as possible. So the way that I previously implemented that was for every step that the maze generator took, it would basically call an external method which I could draw something in. So for example, in a Windows Forms application, I could just change a pixel so that I could see it generating. I could, of course, for the performance benchmark thing, remove that code, but I rarely choose the easy path. So I thought maybe we can do this differently. So initially, I tried like put a null check on this like external call, and see if that would, how that would affect it. But just that null check around the invoke takes about 5% of the whole maze generation time. So I thought, can we do something in C# where we can work around this? And we actually can. So what you can do is you can define an interface iProgress action with an invoke method. And then we define 2 implementations. So one implementation is the noAction struct, and the other one is something where we can do whatever we want in. However, if we then create a generic method where we pass in this struct, it will the compiler will generate 2 instances of this method for both structs. And since the noAction invoke is aggressively inlined, it will inline that call, which doesn't do anything, and it will completely remove that method call. So there's no overhead anymore. So I thought that was a cool one. So that was the first speed up we did there. Then again, Microsoft being Microsoft prefers actual randomness over speed. Why would you do that? You want to create mazes, right? So you don't really care about randomness. So no, it makes perfect sense, of course. But I needed something a bit faster. So I found the XOR shift random, and that is a few % faster than the .NET random. So I implemented that, and that was a few % improvement again. And now we're getting into the hard ones. So what I'll first do is I'll explain the backtrack algorithm in detail, the way that the ultimate implementation works, and then I'll talk about the improved version. So let's look at this. On the left side, we see the current position we're at, and we basically first need to figure out what directions we can go. So the red ones are either outside of the maze or a position we already visited, and the green ones are the ones that we can visit. If you look on the right, what we do is we have a targets array, and an array is faster than just doing list.add all the time, so that's why we use it like this. And within the targets array, at target count, that's 0 here. So we set the targets at position 0. We set that to the green cell above the current position. And here we set it to the green cell above or below the current position. And target count becomes 2 because we had 2 if checks we actually hit. Then we need to choose which one of those directions we go to. So what we do is we do a random on target count, so that can either be 0 or 1. I've now defined this to be 1, which would be going to the bottom. And what we do then is we basically stack here is that whole backtrack list we keep into memory. So we push that on the backtrack list. We set the new target position to true so that it is visited again. And we just take the cell that's in between the previous and the new one, and we also set that to true. So that's the implementation of the current backtrack algorithm. Now, this is the whole code. So there is a problem with this code. And that is if checks. So whenever you have if checks, the CPU basically does a thing called branch prediction, and it tries to predict which path within the if check you will take. But since this is all random, the CPU makes mistakes quite a lot. And if the branch prediction fails, it still figures it out, of course, but it takes a bit of extra time. So a CPU usually is faster in math than in branching. So what I thought was, okay, can we somehow generate a maze generation algorithm without if checks? And I got quite far. So I'll go through the new code, and there is still some hidden if checks in there. If you can find them, congrats. If you can solve them, please come to me, help me. But what I'll do is I'll go through the code again. So let's fill in the values. So we know that valid up is true and valid down is true. What we then do is we convert these booleans to bytes. You can do that with the unsafe method there. And then what we can do is we can just sum them up, all of them, all 4 of them, and then we get the target count again. So that is one part of the whole if check thing solved. Now, we still need to check, or we still need to figure out how we do the direction choosing. And I thought about doing it like this. So again, let's fill in the data that we knew. So we have the random.next, which gives us the chosen direction. We filled in the values that we know, so valid left, valid right is false, and the other ones that we know. And then let's go every step individually. So looking at the first one, so this checks if we're going left, so valid left is false. So actually going left will be false. So countertje, that's Dutch, sorry. That will also remain 0. The same thing happens for actually going right. Valid right is false. The right byte will be 0, so countertje will remain 0. Now it gets interesting, though, for the actually going up byte, because we know that valid up was a valid direction. Let me fill these in. But we also know that we didn't choose that direction. So what we do is, I'll fill them in. So the actually going up and byte are still 0 and false. But since valid up byte was actually true, we increase that with countertje, and now countertje is 1. So that means that for this one, the chosen direction was 1. Countertje is now 1. So that means that the actually going down byte and actually going down will be true. So that means we actually figured out which direction we are going on. What we can then do is we can multiply the actually going down byte with 2, basically, sum that up to the previous position, and that gets us into the new position. So with that, we had like the whole if checklist implementation of the maze completed. So I'll give you a bit of stats here as well. So we went from 3 seconds 27, I think, to 1 second 91. And that is for now the fastest that I've been able to do it, unless you, of course, buy a faster CPU. I also tried this, so that was on .NET 6. I also tried this on .NET 8, 9, and 10. I think this was a different computer, so don't compare the .NET 6 results with the .NET 8 results. But what I find peculiar is that .NET 9 and 10 in my maze generator are always slower than .NET 8 with benchmark.net. And I really can't figure out yet why, so I'll probably create a GitHub issue for that, and hopefully someone at the .NET team can help me with that. Okay. So that was everything regarding the backtrack algorithm, mazes, etc. But I also wanted to share, since we have a bit more time, on some other spin-offs I did. So the algorithm that I spoke about now was backtrack, but there is other algorithms. And one of them is called the division algorithm. And what it does is if you have like, you start with a whole empty white grid, and it just draws a line in the middle with a hole in it. And then it keeps dividing the grid. You can actually build that algorithm in a way that you can just generate a small section of the maze and basically almost have like an infinite maze like that. But since it doesn't really look nice, and since we don't have the path gradient, I don't think it counts. But I'll zoom in a bit. So the reason why we have these zoom in further levels is because, yeah, if you, of course, want the most zoomed out level, you would have to generate all the lower levels. And in an infinite maze, that's going to be a little hard. So I'll just zoom in until we get to the actual maze level. And then what this actually does is it generates the maze level on the fly. And it runs on the Raspberry Pi. But as you can see, so this is the division maze. You already see that it looks a bit different. And if you look here, yeah, this just looks ugly, right? This is not a real maze. But I just wanted to show you. So that's the division maze. The 3D maze, I actually now built a browser version of that as well. And I optimized it a bit more, so even on my own laptop, I think we can go even bigger than the 2000 maze. So let's see when it crashes. So if you ever want to like play around with this, then yeah, feel free to run this. I'll share the URL if you come to me after the session. It's nicely asynchronous, as you can see. Okay, so you can just yeah, play around with this. You can put the camera on the guy. We can make him go a bit faster, if I remember what button that is. Oh, I think I even need a numpad for that. But isn't this beautiful? So that is the 3D browser maze. Dev Image Pyramid, I already spoke about that one. And what I also did was like, I thought, hey, this maze is now 393 gigabytes. Can't I build something to actually optimize the individual PNG images? So then I started working on that for a few years, and then another talk maybe. So before I go to that slide, I also created some maze coasters with unique seed numbers. So they are all guaranteed to be unique. So if someone wants one of these, then feel free to come to me after the session. And what I'll do for the last few minutes is I'll show you a bit of like my initial tool that I made, which is quite cool, which will show you the different algorithms that we have. So let me So who do you think designed this? Let's see. Okay. Okay, so this is the Kruskal algorithm. Ah, this is a bit too big. Let me make it a bit smaller. Yeah, this is the Kruskal algorithm. So this is an algorithm that I think also looks quite cool. The way that it works is it first divides the grid up into like individual cells and then starts randomly combining those. But it always checks if cells are already combined in a different way. So as you can see, it slowly becomes bigger, and it will never combine cells that are already connected through a different path. So this also generates a maze with only one path from any point to any other point. I think this one looks quite nice as well. And then we're getting into the ugly algorithms. Let's see. Let's take, for example, randomized prim. Make the delay 1. So the way that this works is it basically starts at a position and then extends all the different tree elements. But what this ends up with is that basically the path always goes almost through the middle. It's not beautiful. So here you can see if I just do this again and then this, then you can see that almost all the mazes go like straight through the middle. Then let's do the division one. So here you can see that one working. So it just splits the maze into parts basically all the time. And then fills them up. And then just for the heck of it, I also made this was the depth first one. I also made the breadth first one. But the maze is effectively the same. Just looks a bit different. Then we have the hunt-kill algorithm. And I don't even remember how that one worked. Oh, I think this is the one that basically does backtracking, but just starts at a random position. So yeah, it doesn't really bring... Oh, and apparently the path always goes to the right. Then we have LR, which looks as if it's starting the same as the Kruskal algorithm. Let's see how this one works. Oh yeah, this is the one that basically works from the top to the bottom, but also doesn't really generate cool-looking paths. And we have, yeah, that one that's basically the same again. So I'll make them a bit bigger, then we can show a few more. For example, this one. Generation looks quite cool, but again, path always goes through the middle. Division, you always end up with these weird crooked lines. It's just fun to look at, right? Okay, so with that, I think I've talked about everything that I wanted to talk about. So I'd like to thank everyone for their attention, and hopefully you enjoyed it. And feel free to come pick up a maze.